Hello and welcome to this new video. So in this video, I will finish section 2.1 about line integrals. And you can already start solving the first 4 exercises that I will correct next time. Okay? So there are 2 theorems in this video. The first one is the second version of Goursat-Cauchy theorem. And the second theorem is about differentiation under the integral sign. Okay, 2 very useful results that we shall use later. Okay, version 2 is very similar to version 1, except in one point. In version 1, we assume that we have a holomorphic function on omega. In version 2, we assume that f is holomorphic except possibly at one point, but it's continuous on omega. Okay, so continuous on omega, holomorphic on omega without a. Okay, so the assumption is a little bit weaker than the assumption of version 1, and we have the same conclusion. The integral over the boundary of any triangular region on omega of f is 0. Okay, so in principle, it seems that this is a better theorem or a stronger theorem because under weaker assumptions, we have the same conclusion. But we shall see actually later that this is not an improvement actually, because the assumptions that we put on f and omega imply that actually f is holomorphic on omega. Okay, so if you like, a is a removable singularity of f. Okay, but we don't know that yet. We have to prove this version, the stronger version, because we shall use it the next section to prove Cauchy's integral formula. Okay, now we shall deduce version 2 from version 1. Okay, so we have 2 cases. Either the point where there's a problem is in the triangular region or not. If it's not in the triangular region, then the triangular region is contained in omega without a. So if we apply version 1 to f and omega without a, then we get the integral is 0. Okay, so there's nothing new here. So we assume that a is in the triangular region. Okay, so we distinguish here between 3 cases. Either a is a vertex of t, or is interior to t, or is on one side but not a vertex. Okay, so call the vertices v1, v2, v3, and we shall deal first with case 1. So if you relabel the t, you can always assume, if you relabel the vertices of t, you can always assume that a equal v1. Okay, and now I will choose one point on the side v1, v2 that I call a2, and a point a3 on the other side, such that the perimeter of a, a2, a3 of the triangle a, a2, a3 is less than epsilon. Okay, so I will draw a figure to explain that. Okay, so here's my domain. Here's the point A in red, where there's apparently a problem, and this is the triangle. The triangle region is everything inside. So I choose a point A2 on the side A, V2, or V1, V2, and a point A3 on the other side. But I choose A2 and A3 sufficiently close to the vertex A, so that the perimeter of the small triangle is less than epsilon. Okay, fine. And now I join A3 to V2 and I form 2 other triangles. So the triangle V2, A3, A2, V2, A3, A2, and V3, A3, V2, right? And the small triangle. So you observe that these intermediate straight line segments are traveled twice in opposite directions each time. So if you integrate over this triangle, first one, V2, A3, A2, and then over this one, V3, A3, V2, and then on the small one, you get the triangle over the boundary of the triangular region. Okay? And this is something that we already encountered in the proof of version 1. Okay, so the first observation is that the integral over the triangle is the sum of the integrals over the three subtriangles. Now, by version 1, since these two triangles actually are in omega without A, and F is holomorphic on omega without A, so by version 1, the first two integrals are 0 by version 1, right? So we are left with the third integral over the small triangle, okay, whose perimeter is less than epsilon. Okay, now therefore, if you let M be a bound of the modulus of F on the triangular region T, it exists. Why? Because T is compact and modulus of F is continuous, so it's bounded. Okay, so I call the bound M. Of course, I cannot take an upper bound over the small triangle because it's not fixed. I need a constant independent on epsilon. Okay, so this is why I choose the bigger triangle, which is fixed in my reasoning. Okay, so now the modulus of my integral over the boundary of the triangle is equal to the modulus of the third term here, because these two are 0. And now by the fundamental estimate, the modulus of the integral is less than the length of the path, which is the perimeter, times the maximum of the modulus of F over the small triangle, but this is less than the maximum of the bigger triangle T, so it's less than M. Okay, and therefore I get that the modulus of the integral is less than epsilon M. Okay, so since as epsilon was arbitrary, this means that the integral is 0. Okay, but I have to choose M independent on epsilon, right? Depends on the triangle and F. Okay, because if I took the modulus over the small triangle, usually it's something of the form 1 over epsilon. Okay, it's not the case here, but okay, so this is why I took the bound over the bigger triangle and not over the smaller triangle. Okay, and that's it. So this is case 1. Case 2, A is interior to T. So I do a similar construction. I join A to the other vertices so that I get 3 triangles now: V2A V1, V2 V3A, and A V3 V1. Okay, so that once again these sides are traveled twice, so the integral cancel, and therefore the integral over the boundary of this triangle is the sum over the boundary of these 3 triangles. But by case 1, okay, now A is the vertex of this triangle. So by step 1, the integral here is 0. And similarly, the integral over this triangle is 0, and the integral over this triangle is 0. Okay, so when I do the summation, I get that the integral over the big triangle is 0 of F. Okay, and that's it. Case 3 is very similar to case 2. You just do a figure, but then you just have 2 triangles instead of 3, so it's a little bit easier. So you do it. Okay, and this remark I already said it. So we shall prove that the assumptions of the theorem imply that F is holomorphic at A. So A is a removable singularity of F. Okay, so this concludes the first theorem of version 2. The next result, as I said, is the result about differentiation under the integral sign. Okay, so here's the assumption. I have an integral depending on a parameter, but the parameter is a complex variable that varies in an open set omega. And the variable of integration is just a real variable on an interval AB. So when I integrate with respect to t, the result doesn't depend on t, but depends on the parameter z. So I get a function of f of z. Okay. And now, under certain assumptions, I will prove that f is holomorphic and its derivative is the integral of the derivative. So, okay, what are the assumptions? The assumptions are that phi is continuous in both variables jointly and holomorphic with respect to the second variable. Okay, and the derivative with respect to the second variable that I denote by del 2, or if you like, you can denote it by del z if you like, is continuous jointly in both variables. Okay, so the theorem, put simply, the theorem states that the derivative of the integral is the integral of the derivative. Okay, so we can interchange the two operations. And this is something that you should be familiar with from the integration course. But we don't need the Lebesgue theory here, just need the Riemann theory, because everything is continuous and you are working on compact sets, on rectangles, so it's not a big deal. So we can just use the Riemann theory. Okay, so I want to prove that that f is holomorphic at every point z. So I pick a point z in omega, and of course I can choose h small enough so that z plus h, the straight line segment joining z to z plus h is in omega. Okay, we did something similar in previous videos. Okay, so and it's here that we use the fact that omega is open. Okay, we need the fact that omega is open when we talk about holomorphic functions, because when we do Newton's ratio f of z plus h, we must ensure that this z plus h is in the domain of f. Okay, it's not true if z is on the boundary of omega. Okay, so anyway, and now let us call the second integral, the integral of the derivative, let us call it g. Okay, I want to prove that f is holomorphic and f prime of z equal to g. Okay, now what do we have here? We have an integral of a continuous function, of course, depending on a parameter. So it should not be difficult for you to prove that as a function of z, g is continuous. Okay. Of course, you can use the Lebesgue theory, but you don't need to. Just the Riemann theory is enough. Okay. So I will leave it to you as an exercise to test your mathematical skills. And I will prove now that f is holomorphic. So I will consider the Newton's ratio f of z plus h minus f of z over h. Okay? But first, let me do a trick. If you integrate g from z to z plus h, so the variable of integration is called u here because z is fixed. So this is just the integral of the straight line segment joining z to z plus h. If you replace g by its value, you get a nested integral. Okay, but everything here is continuous, and these are just Riemann integrals over rectangles. So Fubini's theorem applies and tells us that we can interchange the order of integration. Okay, now if you look at the inner integral, this is the integral over a path, straight line segment, of a derivative. And by Barrow's rule, this is just equal to the value of phi at z plus h minus the value of phi at z. Okay, t is fixed in this consideration. Okay, and that's it. Now, if I split these two, the first integral is just f of z plus h, and the second integral is just f of z by definition. Okay, and now, so if you divide by h, okay, we get Newton's ratio. Okay, so now it's enough to prove that this quantity 1 over h times this integral tends to g of z as h tends to 0. Okay, so h is the variable here and z is fixed. If I prove that, then we will hit two birds in one stone. So we'll prove that f is holomorphic and its derivative is equal to g of z. Okay, which is the integral of the derivative. Okay, this is not terribly difficult. Okay, let epsilon be given positive as usual. I just use the continuity of g at z, not even uniform continuity. So continuity of g at z means that there exists delta, a positive number delta, such that G of u minus G of z is less than epsilon provided u minus z less than delta. Okay, fine. And now if I take h such that the modulus of h is less than delta, so we do something, a typical technique in analysis here. So we write the difference. Okay, we want to prove that the difference is less than epsilon if h is less than delta. And now here's the trick. This is a constant. Okay, so I can write it as 1 over h times the integral from z to z plus h times g of z du. Okay, because since it's a constant, I can put it outside the integral, and you are left just with h over h. Okay. So and now we put everything under the same integral sign. Okay, and apply the fundamental estimate that the modulus of the integral is less than the integral of the modulus. But if u is between z and z plus h, and modulus of h is less than delta, then u minus z is less than delta, as you may check. So z, u, z plus h are on the same straight line segment, which is very close. The length is less than delta. So this is less than what? So we have so the modulus of h can be put outside. Okay. And now this is less than the integral of the modulus. So I can integrate this inequality. The integral from z to z plus h of this quantity is less than the integral of epsilon from z to z plus h, which is just a constant modulus of h, or just h times epsilon. But when I take the modulus, I get that. Okay? And now this is just epsilon. And that's it. So I proved what? I proved that for every epsilon positive, there exists delta positive such that f of z plus h minus f of z over h minus g of z is less than epsilon if modulus of h less than delta, and this precisely means that f is holomorphic and its derivative is g of z, and you are. Okay, so this concludes this video and concludes section 2.1 about 9 integrals. Okay, so please start doing the exercises from 1 to 4. And thank you for your attention, and see you next time.